Okay, so the next thing we're going to do here is we're going to have a look at a 3D object. So we've got this bracket here, not too complicated, but again, I guarantee the math's going to be annoying. But at least it's homogeneous. It's a steel machine element, so just made of the one type of material, so we're not necessarily, so we're really worried about finding the volumetric centroid, which is going to be equal to the gravitational centroid as well. So we got this thing here. It is already broken up into the question here, kind of already pre-broke it up into the the 4 parts, I guess. So I'll just kind of draw the cutting lines here. So I got kind of this section here. That's cut out. And then we got this square here. And a circle there. And another circle there. So circles are the same size, but I'm still using different colors for them because they do still need to be have their influence calculated individually because of their different location is going to affect the moments. So I think the first things first. Probably the easiest thing to do would be to find the volumes of the individual components. So let's go for the volume of 1. So volume of 1 is going to be 4.5 inches times, what do we got here, 2 inches times 0.5 inches. Which gives 4.5 inches cubed. Two there. Okay, so the kind of surface area there, that's a quarter circle. So pi over 4 times the radius squared. So the radius there is 2 inches. And so that's the surface area kind of right here. And then we get our volume by multiplying that by the thickness, so 0.5 inches. Alright, so pi divided by 4 times 2 squared is 4 times 0.5. So that'll give us 1.57 inches cubed. And then we still need the volume of our little plugs that were bumped out here. So actually, you know what, Dale? Let's call that a negative volume. Why not? Just to be clear. But volume there again. So it's a full. It's not a quarter circle. It's a full circle. So pi times r squared. So the r, it's a 1 inch diameter. So 0.5 inches squared times the thickness. So let's see here, pi times 0.5 to the third. Basically, that gives us a negative 0.392. Sorry, 393 when we round up. page a little bit there. Let's shrink that down, I guess. There we go. And shrink it down some more. Okay. So we got our volumes there. Obviously, our V4 is equal to V3 because they're the same size. So I think the best way to go is just to go about calculating the individual x bar. I'll make it clear. It's a lowercase x bar I vi for each of these, and we'll add them up. So calculate them first. So the x bar. Actually, here, wait. I'll do what I did for the last one, and I'll keep the same colors. So that's this one. That's pink. So x I v or x1 x bar 1 v1. That there. Okay. So again, I guess I'll make our units, our coordinate system a bit more obvious here. Oh, didn't want that to be pink. There we go. Okay, so positive z, positive z, positive z over here, positive x over here, positive y up here. So based upon that, we know that the x bar, so the location of the centroid along the x-axis, going to be just halfway through there, right? For that plate. So that'll be 0.25 inches. And then we times that by our volume. So volume for VI is 4.5 inches cubed. So that'll give us 0.25 times 4.5 is equal to 1.125 inches to the fourth. All right. Let's do all the x bars first, and then we'll move on to the y bars, and then we'll move on to the z bars. I think that's a bit simpler way to go about things. So we got our 2 part here, the little half circle. So x bar 2 v2, that's going to be equal to, well, what's our x bar there? Let's see here. If we can go back, figure out what our centroids are. Okay, so if we've got a centroid for a quarter circle area, it is located at 4r over 3 pi away from the center of the radius. So yeah, that'll be kind of measured from here. So that is the centroid on this figure, but we also need to add to it the distance from the origin to the start of that figure. So basically we need to add this 0.5 inches thickness onto there as well. Okay, so, no, wait. 0.5 inches plus 4 over 3r over pi squared. Wait, no, not squared. No square there. And then that times our 1.57 inches cubed. Okay, so if our radius is 2 inches there, we got 4 times 2 divided by 3 pi. So that's going to give us 0.5 inches plus 0.885 inches. And multiplied out gives us 2.12 inches to the fourth. Okay. All right, and we also got our. No, I didn't actually. How the? I guess I didn't actually write down the volume that we calculated for the. Oh wait, never mind. Sorry, I did. I'm just dumb. Okay. I'll just highlight that there. And in green, underline both there. Sorry about that. Okay, and next we have our little plugs taken out here. So the thing is, for these, the x bar distance so is the same for both of them. It's also the same as for the for VI here, because again they're just kind of punched out of the same shape, as punched out of the same sheet. So that ends up being the same for both of them. So I'm going to start with 3 here. And it's going to be equal to 0.25 inches times, what is the value here? Times negative 393 inches to the fourth. Sorry, to the third. So 0.393 times 0.25. That'll give us a negative 0.098 inches to the fourth. So, relatively minor contribution from that, which isn't too surprising because it's not located, it's not located far from the axis, and so it's not going to be shifting it forward much, and it's also relatively small space, small volume compared to the rest of the object. Anyhow, R4, 1 here. Again, just equals to this same thing. Okay, I guess let's find the volume total. So volume total 4.5 inches to the fourth inches cubed plus 1.57 minus 2 times 0.393. So we're looking at 5.284 inches to the third. That's our V total. And we know that our X bar is just going to be equal to the sum. Oh, I forgot to include the volume terms here. My bad. So yeah, X bar is going to be the sum of our X bar I terms times our VI terms, all divided by the total VI. So what does that end up being? Well, okay, so that's going to be equal to, and scroll down a little bit so you guys can see better. I'll try. Whatever, it's not letting me find the scroll bar. That's really weird. Oh, there we are. There we go. So that term there, 1.125 5 inches to the fourth plus 2.212 inches to the fourth minus 2 times 0.098 inches to the fourth. And all that's going to be over our 5.28. So let's see, what do we got here? 2.12 minus 2 times 0.098. Yeah, 3.049 inches to the fourth divided by 5.284 inches to the fourth. Sorry, to the third. That cancels out to just inch. Which is equal to 0.568 inches. So basically it's hovering just outside the surface of this face here. It's moved enough that it's not that's not actually going to be contained within the volume of the material itself. Which, you know, it happens. Alright, so next up, let's go for our Y bars. So Y bar is going to be equal to the sum of our YI, VI, Y bar VI components divided by the sum of our volume. So let's get on that. So our Y bar 1 V1. Let's have a look. So we're looking at the distance along the y-axis, kind of where along the y-axis the centroid lies. So that's just, it's just a square block, so it's halfway there. So we know that from here to here is 2 inches, so halfway there is going to be 1 inch. 1 inch times the volume of that, which is 4.5 inches to the third. And I hope no one's reaching for their calculator right now. 4.5 inches to the fourth. Okay. No, I tried. I wanted to switch to orange there. There we go. So, y bar 2, b 2. So how about the centroid, the kind of vertical centroid of this this thing here? So again, it's a quarter circle. So it's basically the same. It's the same distance as the x bar term was, at least in relation to the center of the face here. So that's just 4 over 3 r over pi. Now, when we're talking x, it had the 0.5 here, and it was increasing. Here we're talking y. It's actually going down from the 0 point at y. It's moving downwards here from this xz plane. So that'll give us a negative value there, but it starts at the origin here. Like it starts at the xz plane, so there's no offset there. So we just need to throw a negative sign on there, and we got our value. I'm actually just going to do this to move that over a little bit. So that's our y bar, and then we need to plug in our volume as well. So that's again 1.57 inches to the third. So 4 times our radius there is 2 inches. Divided by 3, divided by pi, times 1.57. No. So our r is in inches there, so that works out to 1.33 inches to the fourth. Just double check my calculation there. So we got that. Now we need to find out what we're working with for these ones as well. So for the plugs, that one is also, again, it's also kind of co-located with the y bar for the first bar, because those plugs are kind of taken out directly out of the center of the plate here. So that that line there is located 1 inch below the xz plane. So again, negative value there. So let's just go with, let's start, who goes green first? Yeah, green goes first. So y bar 3 v3 equal to negative 1 inch times, what do we got here? We've got 0.393 inches cubed, but it's a negative volume. And that equals obviously 0.393 inches cubed. So basically what we're saying here is by removing volume from below the y-axis, from below the xz plane, we're shifting the center of gravity upwards. So the exact opposite of what we would have done if we'd added some mass below there. We would have shifted downwards. So yeah, that makes sense. So we got that. And we know that the y bar for our 4 term here is also the same as is its volume. So that'll be the same thing. Oh, sorry. I will fix that because I accidentally put inches cubed instead of inches to the 4th. So we got those values there. Now we can solve for our y bar. Okay, so our y bar overall is going to be equal to the sum of y bar I vi divided by the total volume. So first term 4.5, second term 1.33, and the third term is crap. You know what? I realized I screwed up when doing these calculations. I forgot that this displacement here, that's -2. So that ends up being a negative term. That ended up being a negative term. And I forgot to include the negative term that I had properly included on this one. So these components add up to drag the weight, the center of gravity downwards, and these ones add up to drag it back up again. So my bad. Thankfully, I caught it before embarrassing myself too much further. Negative, and plus 2 times the 0.393. That's all going to be in inches to the 4th. And that is all divided by our total volume. So our total volume, again, still stays the same. That's the 5.284 inches to the 3rd. 5.284 inches to the 3rd. Cross that out, cancels out all but one of the inches. So we're left with inches, which is exactly what we thought we should get. So anyways, -4.5 minus 1.33 plus 2 times 0.393 gives us -5.044, and then all that divided by 5.284 gives us a -0.954 inches. Which I guess shouldn't be all that surprising, that it's basically close to the halfway mark here, but it's going to be slightly higher than that, and that'll be just because of kind of this missing section here. If this semicircle here was square instead, then it just would, everything there would have had a 1 inch term here, and then it canceled out. So we ended up being slightly above the -1 inch mark on the on our y bar. All right. Well, Well, next up, we got one more term left. So let's go for our Z bar. So oh, don't want to switch to the fuchsia yet. Our Z bar is equal to the sum of the Z bar I VI components divided by the total volume. So Z bar I 1, sorry, not I, Z bar 1 V1. Alright, so along the z-axis, the centroid of this thing is located half of 4.5 inches from the xy plane, so 2.25 inches. I will specify that I swear I'm going to get my axes right this time. That's starting from this origin here. Again, right-hand rule, so the z direction is positive in this direction, so that's a positive 2.25 inches. 2.25 inches times our 4.5 inches squared. 4.5 inches to the third. Inches to the third. 4.5 times 2.25 gives us 10.125 inch to the fourth. Alright, we got that. Z bar 2 V2. So this one's easier to do than the previous ones, where it's just a flat plate. Looking down on it, it's it's a flat plate. We're not worried about, so we're just worried about this disc, the centroid through the thickness, which is just going to be half the thickness, which is 0.25 inches. Again, positive in the z direction because we're starting from the axis. We're starting from the xy plane there. There's no offset there. Okay, so that'll be 0.25 inches times its volume, which, if I can recall correctly, is 1.57 inches to the third. Let's double check, make sure I'm right. Yep. 1.57 times 0.25. That'll give us 0.3925 inches to the fourth. Okay, how about our plug here? So centroid of that is located, as you can see, there's a 2-inch gap between the holes, and then there's another 1-inch gap from this hole to the corner here. Let me see, is that, and that's, I will note that that is to this corner here. It is not to the edge, because you'll notice that from here to this distance here, they're giving, that's 4 inches. So there's an additional half an inch past that to get to the XY plane. So the Z bar for this plug here, that's going to be 3.5 inches. .5 inches times the volume of that little space there. So again, a negative volume, negative 0.393. To the third. So that'll be negative 1.376 inches to the fourth. All right, and then next up we got our last plug. Our Z bar 4 for this plug here. Again, 1 inch from there to the corner, and then an additional 1 inch, an additional half inch to get to the origin, gives us a location there of 1.5 inches along away from the XY plane. 1.5 inches. So, and again, I did get the sign convention for all these right because everything, they're all measured from the XY plane in the positive direction of the Z axis. And then times 0.393 inches to the third. That gives us 1.5 times 0.393. We got ourselves a negative 0.58. And no, once we round it, negative 0.59 inch to the fourth. Okay, so I think the next steps from here should be fairly self-explanatory. We just go ahead and add up our Z bar V components. So, and divide that by our total volume, and that gives us our overall Z bar. Wow, I drew 2 sigmas in a row that didn't look absolutely terrible. What are the presses? Okay, so what do we got here? We got 10.1255 plus 0.3925 for the orange. Minus 1.376 minus 0.59, and that's all in inches to the fourth, and then divide that by our area. That's our area. Sorry, not area, volume. Divide that by our volume, we get 5.284 inches cubed. Cancel that out to give us inches. So what do we got here? That is equal to 8.55 divided by 5.284. Equal to 1.62 inches for our Z bar. So back up to our diagram here. So 1.61 inches. So that'll be, let me think here. That will be measured from here. That'll be just kind of past the first hole here. So kind of right about there-ish. Maybe a bit closer to the centroid there. So it's certainly not at the 2-inch mark, which is where it would be if we didn't have this semicircle thing here. The semicircle thing here does manage to drag it a bit to the in the negative Z direction compared to what it would be otherwise. Actually, it wouldn't necessarily be at the 2-inch mark if we didn't have that, because these holes also aren't centered about the centroid of the 4.5-inch bar. They're centered about the centroid of kind of this 4-inch section here. So they're the fact that they are shifted a bit forward compared to the centroid also has some effect in dragging the Y bar back a bit compared to where it would be if it was just this section here. But yeah, overall, not too surprising. And that's about it. As you can see, it is tedious. It's pretty easy to screw up if you screw up your sign conventions, like I almost did there, in the calculations for our Y bar. And it is something that you probably want a computer to be doing most of the time for you. But at the same time, you also at least want to make sure that you have, as an engineer, a reasonably decent intuitive understanding of how these things work. So that's what we're here for.